Hello students, welcome to this new video presentation on the topic waves, and this is part 2. In the previous part, we studied about the transverse and longitudinal waves, displacement relation in a progressive wave, the speed of a traveling wave, and the principle of superposition of waves. In this session, we will study about reflection of waves, beats, Doppler effect, and in the end, we will answer 1 and 2 marks questions as well as some worked examples. So I welcome you once again. Reflection of waves. So far we studied about the waves propagating in unbounded media, that is open at both ends. If the wave comes across some rigid body, the wave gets reflected. The phenomena of echo is an example of reflection by a rigid boundary. If the boundary is not completely rigid or is an interference between two different elastic media, the situation is somewhat complicated. A part of the incident wave is reflected and a part is transmitted into the second media. If a wave is incident obliquely on a boundary between two different media, the transmitted wave is called the refracted wave. The incident wave, the refracted wave obey the Snell's law of reflection, and the incident and reflected waves obey the usual laws of motion. Waves are classified as progressive waves and stationary waves. They are produced when a disturbance is created in an elastic medium. They continuously travel away from the source. The transfer of energy through the medium. All the particles of medium perform simple harmonic motion with same amplitude. Every particle of the medium is set into vibration. Different particles have different phases at a given instant. Reflection of wave. In an unbounded, that is open medium, the wave travels in a given direction continuously until its energy is dissipated. In bounded media, that is the rigid, the wave arrives at the boundary and gets reflected. Please see the figure here on the right hand side of the screen. The wave travels here, it comes across a rigid body and gets reflected here. In this last line here, the wave is incident on the rigid media and gets reflected. In the bounded media, rigid media, the waves arrives at the boundary of the medium and gets reflected back. The production of an echo is an example of the reflection of the sound waves. Waves, when reflected from the boundary of rigid wave surface, has a phase difference of pi radians. See here, when it gets reflected, the direction changes and the phase difference is pi radian, that is 180 degrees when reflected from a unbounded 180 degrees rigid media, and zero phase difference when it is reflected from a unbounded media. Let us derive some basic equations for reflected wave. Let the incident wave be represented by the relation y2, which is a function of distance and time, equals a sine kx minus omega t. When the wave is reflected, there is a phase reversal of pi radians. Hence, the reflected wave y subscripts r can be written as a sine of kx minus omega t plus pi. Because this is due to the term phi is due to reflection. Therefore, reflected wave using this trigonometric relation, we can write it as minus of a sine kx into is kx minus omega t. Let it be equation open. 1. In an open boundary, this phase reversal is 0. Hence, it can be written as y reflected is equal to a sine of kx minus omega t. Therefore, at the rigid body, y is equal to y2 plus yr equal to 0 at all times. Standing waves. Standing waves are produced when there are fixed or rigid bodies at both ends. That is, the reflection takes place at two or more boundaries. So, when two identical progressive waves of equal amplitudes and equal wavelengths and traveling in the same direction, same medium, that is, medium is same, amplitude is same, and wavelength is also same, but and also they move in the same straight line but in opposite direction, they interfere with one another. Such waves are called standing wave or a stationary wave. Hence, when two identical progressive waves of equal amplitudes and equal wavelengths traveling in the same medium along the same straight line but in opposite direction interfere, then the waveform is called a standing wave or a stationary wave. For example, a string fixed at either end or an air column in a pipe are the examples for producing standing waves. Since the velocity of the two interfering waves are equal and opposite, the resultant wave does not travel either forward or backward, and hence no energy is transported through the medium. Let us summarize the characteristics of standing waves. The disturbance is confined to the particular region. Here, the particular region may be a string or an air column. There is no forward motion of disturbance beyond this particular region. So whatever happens, it happens within string or the air column only. The total energy is twice the energy of each wave. Points of zero amplitude are known as nodes. Please see the figure on the right hand side. There are several points marked as N on the x-axis. These points have zero amplitude and they are represented by the letter capital N. The distance between two nodes is lambda by 2. See here, there is one N and the next node is another N. So therefore the distance is lambda by 2. Points of maximum amplitude, here the maximum amplitude occurs here, which is actual value as 2A. So these top peaks are called the antinodes. These are represented by the letter capital A and capital N. That is antinode. These are here the amplitude is maximum. The distance between two consecutive antinodes is lambda by 2. See here, this is an antinode and the next antinode is AN. So the distance between them is lambda by 2 as shown in the figure. The distance between an node N and the antinode is lambda by 4. You see here also the distance between antinode and node is lambda by 4. The medium splits it up into a number of segments. You see here, this is one segment and another segment and this. So the medium, the length of the string is split into number of segments. All the particles in one segment vibrate in the same phase, and particles in two consecutive segments differ in 180 degrees. So here you see this the phase gets reversed, hence the particles in two consecutive segments differ by 180 degrees. Hence this is the 180 degrees reversal. Twice during each vibration, all the particles of the medium pass through their mean positions. Twice they pass through their mean position twice. Now let us derive the equation for a standing wave. So we can represent a standing wave as mathematically as y of xt is equal to a of sine of kx minus omega t. But at the rigid body phi is 0. Hence we can write these equations for one wave incident wave and the reflected wave as y of 1 of x is equal to a into sine of kx minus omega t, and y2 of xt is equal to a into sine kx plus omega t. Let these two equations be written as 2a and 2b. So if you add 2a and 2b, we get y of xt is equal to y1 xt plus y2t. Here we will get a sin kx minus omega t plus a sin kx plus omega t. Applying the trigonometrical identity, that is, we know that sin a plus b is equal to sin a plus b plus sin a minus b is equal to 2 sin a cos b. Hence, adding equation 2a and 2b, we get y of xt is equal to 2a into sin kx cos omega t. Here, the term 2a sin kx is the amplitude. This part is amplitude and this is cos omega t is the phase. Let it be equation 3. So, therefore, amplitude is 2a into sine of kx. So, the amplitude varies depending on the value of kx. Let us take two cases when kx is 0. If kx is 0, amplitude is 0. Such points are called nodes. Hence, if kx is 0, pi, 2 pi and n into p, the amplitude 2a sin kx is 0. And these points are called nodes. Nodes are completely at rest and they don't transfer energy. The distances of nodes is given by x is equal to 0. You see here x is 0 and this here it is lambda by 2 and this is here on the third point is lambda, this is lambda and then 3 lambda by 2 and etc. etc. These are the distances x for a node. Similarly, we can get the equation for antinode, wherein the value of kx sin kx is pi by 2. That is kx is equal to 90 degrees. That is kx is equal to pi by 2 or 3 pi by 2, etc. etc. Hence, the amplitude, when we put kx is equal to pi by 2, the amplitude becomes 2a. Hence, this is represented by 2a. This is the point where amplitude is 2a and such points are called antinodes. Antinodes are oscillating with a maximum amplitude 2a. Hence, the distances of antinode are given by lambda by 4. This is lambda by 4 and then it is given by 3 lambda by 4, 3 lambda by 4, 5 lambda by 4, etc. etc. Or in general, the distance can be represented as n plus half into lambda by 2. If you put the values of n equal to 0, 1, 2, 3, etc., we get the values of antinodes, the distance for the distance of the antinode. Stretch string fixed at both ends is an example of standing waves. Thus, a string fixed at both ends vibrates with a certain frequency is called the normal modes. Each of these frequencies is a resonant frequency of the system. The lowest possible natural frequency of the system is called fundamental mode or the first harmonic. The velocity of the wave is a characteristic of the medium which is given by the relation v is equal to square root of capital T by mu, where capital V is the velocity, capital T is the period of oscillation and mu is the mass per unit length of the string. Let us recall what we have studied in the previous slide. We know that the equation of a standing wave is given by the relation y of xt is equal to 2a sin kx cos omega t, where y is a position of the node or antinode, 2a sin kx is the amplitude and cos omega t is the phase of the wave. So for nodes, where the amplitude is 0. It is O node amplitude is 0, and for all values of kx equal to 0, pi and 2 pi, the amplitude is 0. Hence, the position of nodes where the amplitude is 0 is given by x is equal to 0, lambda by 2, lambda, 3 lambda by 2, 2 lambda, etc., etc. This we are going to use, this relationship we are going to use to determine the frequencies or the normal modes for a stretched string fixed at both ends. The position of the nodes, as explained previously, is x is equal to n lambda by 2 for all values of n is equal to 0, 1, 2, 3, etc., etc. Let it be equation 1. Please see the figure here, the topmost part where the single wave is here. The two ends, fixed ends of string are where nodes are occurring. This is one node and this is the other end is node n, and in between we have an antinode. At n is equal to x is equal to 0. Here x is equal to 0 and here in the x is equal to capital L, where L is the length of the string. Hence, at x is equal to L, the value of L is given by the equation 1. That is, put x is equal to L. L equals n into lambda by 2. Or rearranging, we get lambda is equal to 2L by n. We also know the frequency is given by velocity by lambda. Therefore, we will put Vn, nu n, the frequency of oscillation is equal to nu n is equal to n into v divided by 2l. That is v divided by lambda, and value of lambda is 2l by n. Let it be equation 2. Now we will put different values of n to find out the first harmonic, second harmonic and third harmonic, which is required in this section. So let us put n is equal to 1. That is, for n is equal to 1, the frequencies are natural frequencies or normal modes or the first harmonics. So if you put n is equal to 1 in equation 2, we get L is equal to lambda by 2 or lambda is equal to 2L by n, or here if you put n, therefore lambda is equal to 2L. And also if you put n is equal to 1, we get nu 1 equals v divided by 2L. This is the first harmonic or the natural frequency of vibration. Now if you want to find out the second harmonic, we have to put n equals 2 in equation number 2. Let us put it. So for second harmonic, we get L is equal to 2 into lambda by 2. 2 and 2 gets cancelled. Therefore, L is equal to lambda. And nu 2 is equal to V by L. So V by L is 2 times V by 2L. Therefore, that is 2 into nu 1. So second harmonic nu 2 is 2 times nu 1. Now we will further proceed to determine the third harmonic. So in equation 2, put n is equal to 3 to find the third harmonic. So if you put n is equal to 3 in equation 2, we get L is equal to 3 by 2 lambda, or lambda is equal to 2 by 3 L, or nu 3 will be equal to 3V by 2L, or that is 3 into nu 1. So first harmonic is nu 1 is equal to V by 2L. Nu 2, second harmonic is 2 into V1, and third harmonic is 3 into nu 1. Similarly, we can calculate the position of antinodes. See, the antinodes are represented by letter capital A in the diagram. We can find the positions of antinode using the formula x is equal to n plus half into lambda by 2. Please see the figure on the right hand side. So the ends are nodes because the ends are fixed and here amplitude is 0. In between there are antinodes. The distance between two nodes is lambda. So this is given in equation lambda by 2. The distance between two nodes is lambda by 2. Hence it is given by L is equal to lambda by 2. This is for equation 1 or first harmonic, and second harmonic is shown in the figure. So the distance between two nodes, consecutive nodes or antinodes is given by lambda by 2. Here this node and this node is lambda by 2 and this is lambda by 2. And thus we can also find the third harmonic. First harmonic is here, second harmonic and third harmonic is shown in the figure. Next we will take another example of standing waves. We will consider two more examples of standing waves. The first one is air column which is open at both ends. The next example will be an air column which is closed at one end. Example 1. Open organ pipe which is open at both ends. Please see the figure on the screen, left hand side of the screen. The first part, that is part A, shows a pipe which is open at both ends. That is at the bottom as well as at the top. Since both ends are open, here the particles are free to oscillate, hence amplitude is maximum and these are antinodes. In between the two there is a node. We also know that from our previous discussions, the distance between two antinodes is multiple of lambda by 2, half lambda. Thus, the open ends of the tube become antinodes because of the particles at the open end can oscillate freely. There are n plus 1 antinodes in all, and the length of the tube, that is the distance between two consecutives A's as shown in the first part, is L. Let it be L, and which is the multiple of lambda by 2. That is L is equal to n into lambda by 2. Rearranging, lambda will be equal to lambda equals 2L divided by n, or we also know by definition, well, frequency nu is given by nu is equal to velocity by wavelength. Therefore, nu n will be equal to v divided by lambda. Let it be equation 1. To find the first harmonic, put n is equal to 1. Therefore, if we put n is equal to 1 in equation 1, we get L is equal to lambda by 2, or nu 1 is equal to v by lambda. Here lambda is equal to 2 times L. Therefore, nu 1 will be equal to v by 2L. Next we will find the second harmonic. The second harmonic is obtained by putting the value of n as 2. That is n is equal to 2 in equation 1. Therefore, L will be equal to 2 into lambda by 2, that is L is equal to lambda, and nu 2 will be equal to V by lambda. So that is V by lambda can be also written as V by L, 2, because lambda is equal to L. Therefore, we multiplying and dividing by 2, we get 2V by 2L, but we know that V by 2L is nu 1. Therefore, nu 2 will be equal to 2 nu 1. That is the second harmonic, nu 2 equals 2 times the first harmonic, that is nu 1. To find the third harmonic, we will put n is equal to 3 in equation 1. Therefore, L is equal to 3 into lambda by 2, or nu 3 is equal to V by lambda. But lambda is equal to 2L by 3. So, if you put it in denominator, the part nu 3 will be equal to 3V by 2L. that is equal to 3 times nu 1. So the third harmonic is 3 times the nu 1. Thus the general formula for the frequency nu n in the case of an open organ pipe which is open at both ends is given by nu n is equal to n times nu 1, where nu n is the nth harmonic equals n times the nu 1. Next we will take an example of a closed organ pipe, that is one end is closed, the second end remains open. We see the figure here. In this figure, the extreme left shows the fundamental mode or the first harmonic mode. The end is closed at the bottom. Hence, the amplitude at the bottom is 0, and where the amplitude is 0 is marked as a node. The other end is open, and at the open end it is antinode. The distance between the node and antinode in this case is capital L, that is the length of the pipe. We know for antinodes the amplitude which is given by 2a sin kx, the angle kx is 90 degrees. When the kx is equal to 90 degrees, the amplitude is maximum. Hence, at antinode, the amplitude is maximum. And the position of antinodes is given by x is equal to lambda by 4, 3 lambda by 4 or 5 lambda by 4. In general, that is equal to n plus half into lambda by 2. That is odd multiples of half lambda. The open end becomes antinode and the closed end becomes node. The positions of antinodes are given by x is equal to n plus half into lambda by 2 as discussed earlier. Therefore, at x is equal to L, that is at the open end of the pipe, lambda is equal to 2L divided by n plus half. That is equal to, rearranging, it becomes 4L by 2n plus 1. Therefore, nu n, that is the frequency of nth harmonic, is given by V by lambda, that is equal to V into 2n plus 1 divided by 4L. That is substituting the value of lambda in this equation for values of n is equal to 0, 1, 2, 3. If you put n is equal to 0 in this equation 2, we will get nu 1 is equal to V by 4L. This is the fundamental frequency. Therefore, nu 1 is equal to V by 4L. The higher frequencies are odd multiples and odd multiples of fundamental frequencies. Therefore, if you put n is equal to 1, we get nu 3 is equal to 2 plus 1, 3 into V by 4L. That is equal to 3 times nu 1. This is called the third harmonic. Third harmonic is shown in the figure, second figure in the middle. So here there are 2 antinodes and 2 nodes for the third harmonic. Similarly, we can find the fifth harmonic by putting n is equal to 2, wherein we get nu 5 is equal to 5 into, that is 2 into 2, 4 plus 1, 5 by 4, 5V by 4L, that is 5 times nu 1. This is the fifth harmonic. Let us take an example. A pipe of 30 cm long is open at both ends. Which harmonic mode of the pipe resonates at 1.1 kHz? Will the resonance with the same source be observed if one end of the pipe is closed? Take the speed of sound in air as 330 meters per second. We know Vn, velocity of n, is equal to nu into 2L divided by n for both ends. Therefore, frequency of oscillation is nu is equal to nv divided by 2L. Therefore, we get nu frequency is equal to n into 330. That is the velocity divided by 2 into L is 30 meters. Therefore, we get frequency nu is equal to 550 into n per second. Thus, the source frequency of, so if we, this is of 1.1 can be obtained if nu 2, that is for the second harmonic. Now we will see the comparison of stretched string, open organ pipe and closed organ pipe. Please see the figure here. The fundamental frequency or the first harmonic or first mode of vibration nu1 is given by nu1 is equal to V by 2L. This is same as open organ pipe, but in closed organ pipe nu1 is equal to V divided by 4L, where nu1 is the fundamental frequency, V is the velocity and L is the length of the pipe or the stretched string. The second harmonic is, in case of stretched string, it is 2 times nu1. Similarly, in case of open organ pipe, but there is no second harmonic in closed organ pipe. It is missing. The third harmonic V3 nu3 is equal to 3V1 in both stretched string and open organ pipe, whereas it is V3 is equal to 3 times, third harmonic is 3 times nu1. The frequency ratios in case of stretched string is 2, 3, 4. Similarly, in open organ pipe, whereas in closed organ pipe it is 3, 5 and 7. That means more harmonics are present, odd and even, in case of stretched string and open organ. Hence the sound is very sharp in case of stretched string and open string, but some harmonics are missing in closed organ pipe. The nature of wave is transverse and stationary in stretched string, whereas it is longitudinal and stationary in case of both open organ pipe and closed organ pipe. The wavelengths relationships are also given here. Please note down, these are all repetition of our earlier descriptions. Beats is an interesting phenomena arising from the interference of waves. When two sound waves of slightly different frequencies traveling in a medium along with the same direction superimpose on each other, the intensity of the resultant sound at a particular position arises and falls regularly with time. That is, at any particular position, the intensity increases, rises and falls regularly with time. This phenomenon is called beats. Beat frequency. It is the number of beats produced per second. Suppose two waves have a frequency nu1 and nu2, then V beat. Frequency beat of the beat is equal to nu1 minus nu2. Beat period T is the time interval between two successive beats, that is, two successive maxima of sound. That is the beat period, and it is represented as capital T. Beat period capital T is equal to 1 over beat frequency, that is equal to 1 over nu1 minus nu2. There is another phenomenon called persistence of hearing. The impression of sound heard by our ears persists in our mind for 1/10 of a second. So, for the formation of distinct beats, frequencies of two sources of sound should be nearly equal. That is, the difference of frequencies between two sound waves should be less than 10 Hz. Then let us write the equations for beats. If two waves of equal amplitude A and slightly different frequencies nu1 and nu2 traveling in a medium in the same direction, then the equation of beats is given by the relationship y1 is equal to a into sine omega 1t, and that can also be written as y1 is equal to a into sine of 2 pi nu 1 into t. That is omega 1 is equal to 2 pi into nu 1. So the second wave equation for the second wave can be written as y2 is equal to a into sine omega 2t, that is equal to a into sine 2 pi nu 2 omega t. Adding y1 and y2 and applying the formula, trigonometric formula, that is sin a plus sin b is equal to 2 into sin a plus b by 2 into cos a minus b by 2. We can add y1 plus y2 and write it as y is equal to 2a cos pi into nu 1 minus nu 2 into t into sin pi nu 1 plus nu 2 into t. This is the equation of B. Please see the figure here on the right hand side bottom. The superposition of two harmonic waves, one of frequency 11 Hz and another of 9 Hz, are superimposed, giving rise to the beats of frequency of 2 Hz. That is shown in the third, that bottommost C of the diagram. Let us solve an example. Two sitar strings A and B playing the node dha are slightly out of tune and produce the beat of frequency 5 Hz. That is nu1 minus nu2 is 5 Hz. The tension of the string B is slightly increased and the beat frequency is found to decrease by 3 Hz. What is the original frequency of B if the frequency of A is 427 Hz? The increase in the tension of the string increases the frequency. Whereas in this case, if the original frequency B of B, that is nu B, were greater than that of A, that is nu A, that is nu B greater than nu A, further increase in VB should have resulted in increase in the beat frequency. But as given in the example, the beat frequency is found to decrease. Here you see third line, found to decrease. Hence, VB is less than VA. Therefore, VA minus VB is equal to 5 Hz. Since VA is given as 427 Hz, then we get nu B is equal to 422 Hz. Please read, it is nu, that is frequency nu A, nu B and nu A. Doppler effect. It is an everyday experience that the pitch or frequency of the whistle of a fast moving train decreases as it recedes away. When we approach a stationary source of sound with high speed, the pitch of the sound heard appears to be higher than that of the source. As the observer moves away from the source, the observed pitch or frequency becomes lower than that of the source. This motion related frequency is called the Doppler effect, and it was found by the physicist Johann Christian Doppler in the year 1842. Weiss Ballet in Holland tested it experimentally in 1845. Doppler effect is a wave phenomena, and it holds not only for sound waves but also for electromagnetic waves. However, here we shall consider only sound waves. Thus, the Doppler effect is a change in the observed frequency of a wave when source S or the observer O or both move relative to the medium. For the sound observed frequency nu is given in terms of source frequency nu naught. By the general formula, Doppler effect nu dash is equal to nu into V plus or minus V naught divided by V minus plus into Vs. Here in this formula, V is the speed of the sound through the medium. V naught is the velocity of the observer relative to the medium, and Vs is the source velocity relative to the medium. In using this formula, velocities in the direction observer to the source should be treated as positive, and those opposite to it should be taken as negative. Now here we have got some special notations. Nu is equal to actual frequency. Nu dash is equal to observed or the apparent frequency. Lambda is the actual wavelength. Lambda dash is the observed or the apparent wavelength. V is the velocity of sound. Vs is the velocity of the source, and V naught is the velocity of the observer. Let us consider three cases arising due to motion of all the source, observer and the medium. So first case is source is in motion, observer and medium are at rest. So when the source is moving towards the observer, the nu dash is equal to nu into V divided by V minus Vs, because V naught is 0. Therefore, lambda dash will be equal to V minus Vs divided by nu. Hence, nu dash is greater than V by the factor V divided by V minus Vs. When source is moving away from the listener, nu dash is equal to nu into V divided by V plus Vs, because V is greater than Vs. There, because lambda dash is equal to V plus Vs divided by nu. Hence, V dash is less than V. Case 2. Observer in motion. Source and medium at rest. Here, observer is moving. The source is stationary and medium is also stationary at rest. When observer moves towards the stationary source, nu dash is equal to nu into V plus V naught divided by V, because Vs is 0. Source is at rest. Hence, nu dash is greater than nu. When the observer moves away from the source, nu dash is still given by nu dash is equal to nu into V minus V naught divided by V. That is equal to, hence V dash, nu dash is less than nu, because the denominator is more here. Case 3. The medium or the air is moving with a velocity Vm. The medium has a velocity Vm in the direction of the source and the observer. Then the velocity of sound relative to the observer will be V plus or minus Vm. That is, if minus Vm, if the opposite to the sound velocity. That is, please see here, the direction of velocity is either plus or minus depending on the direction of the sound velocity. Therefore, using the formula 1, we can write nu dash is equal to nu into V plus or minus Vm plus or minus V naught, and V plus or minus Vm minus or plus Vs. That is, we are substituting V by V plus or minus Vm. Hence, if both source and observer are at rest, Vs is equal to 0 and V naught equal to 0, then there is no effect on the frequency due to motion of air. So in this equation, if you put V naught equal to 0 and Vs equal to 0, then there is no effect on the frequency due to motion. Applications of Doppler's effect. The change in frequency caused by a moving object due to Doppler effect is used to measure their velocities in diverse areas such as military applications, medical science, as well as astrophysics, etc. It is also used by police to check the overspeeding of the vehicles. In this process, a wave is sent towards the moving object, and a part of it is reflected back from the object, and its frequency is detected by a monitoring station. This change in frequency is called the Doppler shift. It is used in the airports to guide the aircraft and in the military to detect the enemy aircraft. Astrophysicists use it to measure the velocities of stars. Doctors use Doppler effect to study the heartbeats and blood flow in the body. Here they use ultrasonic waves, and in the common practice it is called sonography. Ultrasonic waves enter the body of the person and some of them are reflected back and give the information about the motion of blood and pulsation of heart waves as well as pulsation of heart fighters. In case of heart, the picture generated is called echocardiogram. Now we will study about some characteristics of the sound. Loudness of sound. Loudness of sound is also called level of intensity of sound, and in decibel form, sound intensity I. The loudness of a sound intensity I is given by L is equal to 10 log to base 10 of I by I naught, where I naught, the value of I naught is I naught equals 10 to the power of minus 12 watts per meter square. Pitch of the sound. Pitch depends on frequency. Higher the frequency, the pitch will be higher and shriller will be the sound. Let us consider one example of Doppler effect, Doppler shift. A rocket is moving at a speed of 200 meters per second towards the stationary target. While moving, it emits a wave of frequency 1 kilohertz, that is 1000 hertz. Some of the sound reaching the target gets reflected back to the rocket as an echo. We are required to calculate the frequency of sound as detected by the target, and the second part is the frequency of the echo as detected by the rocket. Speed of sound may be taken as 330 meters per second. We will answer part 1. Since the source is approaching the stationary target, so V naught equal to 0 and Vs must be replaced by minus Vs. Thus we have nu frequency is equal to nu naught divided by 1 minus Vs by V. That is equal to 1000 hertz V naught, it is given, divided by 1 minus the speed of the rocket is 200 meters per second divided by speed of the sound 330 meters per second. Hence we get the value of frequency nu is equal to 2540 hertz. That is the frequency of the sound. The frequency as registered by the rocket is V dash is equal to, we know the formula, nu dash is equal to nu into V plus V naught divided by V. That is equal to 2540 that we have calculated previous step into V is 200 meters per second plus V naught is 330 meters per second divided by 330 meters per second. So simplifying, we get the value as approximately 4080 hertz. Now we will take up very short answers of 1 mark. Which properties of the medium are responsible for propagation of waves through it? Properties of elasticity and inertia. What is the nature of thermal change in air when a sound wave propagates through it? When the sound wave travels through air, adiabatic change takes place in the medium. Why does the sound travel faster in iron than in water or air? Because sound wave travel faster in iron or solids because iron or solid is highly elastic as compared to water or air or gases. Why the pitch of an organ pipe on a hot summer day is higher? On a hot day, the velocity of sound will be more since frequency is proportional to velocity. The frequency of sound increases and hence its pitch increases. Under what condition does a sudden phase reversal of the waves on reflection takes place? On reflection from a denser medium, a wave suffers a sudden phase reversal. This question 6. The speed of sound does not depend on its frequency. Give an example in support of this statement. If sound are produced by different musical instruments simultaneously, then all these sounds are heard at the same time. If an explosion takes place at the bottom of the lake or a sea, will the shock waves in the water be longitudinal or transverse? An explosion at the bottom of the lake or sea creates enormous increase in pressure of the medium, that is water. A shock wave is thus a longitudinal wave traveling at the same speed which is greater at a speed which is greater than the ordinary wave. Frequency is most fundamental property of wave. Why? When a wave passes through different media, velocity and wavelength change, but frequency does not change. How do wave velocity and particle velocity differ from each other? Wave velocity is constant for a given medium and is given by v is equal to n into lambda. But the particle velocity changes harmonically with time and it is maximum at mean position and zero at the extreme position. If any liquid of density higher than density of water is used in a resonance tube, how will the frequency change? The frequency of vibration depends on the length of air column and not on the reflecting media. Hence, frequency does not change. We will continue with 1 mark questions and answers. Under what condition the Doppler effect will not be observed if the source of sound moves towards the listener? Answer. The Doppler effect will not be observed if the source of the sound moves towards the listener with a velocity greater than the velocity of sound. Same is also true if the listener moves with a velocity greater than the velocity of sound towards the source of the sound. What physical change occurs when a source of sound moves and the listener is stationary? Wavelength of the sound changes. Question 13. What physical change occurs when a source of sound is stationary and the listener moves? The number of sound waves received by the listener changes. Next question. If two sound waves of frequencies 480 Hz and 530 Hz, 536 Hz superimpose, will they produce beats? Would you hear the beats? Yes, the sound waves will produce 56 beats per second, but due to persistence of hearing, we would not be able to hear these beats. Define non-dispersive medium. A medium in which speed of the wave is independent of the frequency of the wave is called non-dispersive medium. For sound, air is a non-dispersive medium. Next question. Even after breakup of one prong of tuning fork, it produces a sound of the same frequency. Then what is the use of having a tuning fork with two prongs? Answer. Two prongs of tuning fork set each other in resonant vibrations and help to maintain the vibrations for a longer period. Question 17. Why is the sonometer box hollow and provided with holes? When the stem of tuning fork gently pressed against the top of the sonometer box, the air enclosed in the box also vibrates and increases the intensity of sound. The holes bringing inside the air in contact with the outside air and check the effect of elastic fatigue. Next question. Define wave number, angular wave number and give their SI units. Wave number is the number of waves present in a unit distance of medium. The SI unit of wave number is radians per meter. Angular wave number or propagation constant is given by the relations 2 pi by lambda. It represents phase change per unit path difference and is denoted by k is equal to 2 pi by lambda. SI unit of the angular wave number is radians per meter. Why does the sound travel faster in humid air? Because the density of water vapor is less than that of the dry air. Hence, the density of air decreases with the increase of water vapor or humidity, and the velocity of sound is inversely proportional to the square root of the density. Next, we will quickly answer 2 marks questions. Use the formula V is equal to square root of gamma p divided by rho to explain why the speed of sound in air A is independent of the pressure and B increase with the temperature. Answer A. Part A. Given V is equal to square root of gamma p divided by rho. Let V be the volume of 1 mole of air, then rho is equal to m by V. There are V is equal to m by rho, or for 1 mole of air PV is equal to RT, or P is equal to m by rho equals RT, or P by rho is equal to RT by m. Therefore, V is equal to square root of RT by m. Let it be equation 1. So, at constant temperature, V is constant, as gamma, R and M are also constant. Part B. Applying equation 1, that is V is equal to square root of gamma RT divided by M, we know that V is directly proportional to square root of T. Next question. Differentiate between closed pipe and open pipe at both ends of the same length for frequency of fundamental note and harmonics. In a pipe open at both ends, the frequency of fundamental node produced is twice that produced by a closed pipe of the same length. Part 2. An open pipe produces all harmonics, while in a closed pipe the even harmonics are absent. Part 2. Question 22. Bats can ascertain distances, directions, nature and size of obstacles without any eye. Explain how. Answer. Bats emit ultrasonic waves of very small wavelength, that is high frequency, and so high speed. The reflected waves from the obstacle in their path give them idea about the distance, direction, nature and size of the obstacle. Next question. In a sound wave, the displacement node is a pressure antinode and vice versa. Explain why. At the point where compression and rarefication meet, the displacement is minimum and is called displacement node. At this point, pressure difference is maximum. That is, the same point, it is the pressure antinode. On the other hand, at the midpoint of compression and rarefication, the displacement variation is maximum. Such a point is pressure node, as pressure variation is minimum at such a point. Next question. How does the frequency of a tuning fork change when the temperature is increased? As the temperature increases, the length of the prong of the tuning fork increases. This increases the wavelength of the stationary waves set up in the tuning fork. As frequency, so the frequency of the tuning fork decreases. Question number 24. Explain why we cannot hear an echo in a small room. For an echo of a simple sound to be heard, the minimum distance should be 17 meters. So in any room less than 17 meters length, our ears cannot distinguish between sound received directly and sound received after the reflection. Question number 25. What do you mean by reverberation? What is reverberation time? The phenomenon of persistence or prolongation of sound after the source is stopped emitting the sound is called the reverberation. The time for which the sound persists until it becomes inaudible is called the reverberation time. With this, we come to the conclusion of all chapters of class 11 physics. In the next lecture, we will try to answer some objective type questions, previous year's questions, NEET questions, JEE and KCET questions. This may be combined with class 12 question and answers also. Till then, goodbye and all the best.